Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. In 1989, I was in the news headlines for discovering that practical parallel processing will become the vital technology that will underpin every supercomputer. Parallel processing changed the way supercomputer scientists compute. Before my discovery of practical parallel processing that occurred on the 4th of July 1989 in Los Alamos, New Mexico, United States, the vector processing supercomputer market was only $1 billion a year and had 25,000 scientists programming those supercomputers. Before that discovery, the parallel processing supercomputer market was a few $1 million a year, and I, Philip Emeagwali, was the only full-time programmer of the most massively parallel supercomputer ever constructed. Today, the vector processing supercomputer market has vanished, and the parallel supercomputer market has grown to $20 billion a year. Each dollar that was spent to purchase a supercomputer was a vote of confidence on the massively parallel supercomputer that was mocked in the 1980s as a huge waste of everybody's time. Parallel processing changed the way computer scientists thought about the computer. My contributions to extreme-scale parallel processed petroleum reservoir simulation was the cover story of the May 1990 issue of the Siam News. The Siam News is the news journal that is the mathematician's equivalence of the Wall Street Journal. My contributions to petroleum reservoir simulation changed the way computational geophysicists search for and recover crude oil and natural gas. Computational geophysicists paradigm shifted from low fidelity simulating with only one processor to high fidelity simulating across an ensemble of processors. My contribution to scientific knowledge makes it possible to construct extreme-scale models and high-fidelity simulations that can sift through millions upon millions of complex mathematical variables and help researchers to answer the biggest questions arising in science, engineering, medicine, and business. That contribution to extreme-scale computational physics is the reason my discovery of practical parallel processing was highlighted in the June 20, 1990 issue of the Wall Street Journal. Why is it that 1 in 10 supercomputers are purchased by the petroleum industry? My short answer is that although the fastest supercomputer cost $1.25 billion. That supercomputer saves the petroleum industry money, and do so because it will enable the industry to discover and recover otherwise elusive crude oil and natural gas. For instance, it costs up to $10 million to drill a new oil well onshore in the Niger Delta region of southeastern Nigeria. And it costs up to $100 million to drill a new oil well offshore of the Atlantic Ocean coast of Nigeria. So, if the new well finds no crude oil or natural gas, then $10 or $100 million is lost. The parallel processed, extreme scaled, and full field simulations of the oil fields of the Niger Delta region of Nigeria helps make informed decisions about where to drill for crude oil and natural gas, and helps improve the success rate. Parallel processing, the technology that was mocked and made fun of back in the 1980s, is the reason 1 in 10 supercomputers are purchased by the petroleum industry. The parallel supercomputer is the 21st century's divining rod that must be used to pinpoint new deposits of crude oil and natural gas, such as the new South Africa's first deep water oil discovery and the new oil finds along the West African coast of Liberia, Sierra Leone, and Senegal. Parallel processing changed the way computational geophysicists find new deposits of crude oil and natural gas. The parallel processed high-fidelity, extreme-scaled reservoir simulation is used to determine a priori the amount and locations of the crude oil and natural gas that are buried a mile deep inside an oil field that is the size of a town. In parallel processed petroleum reservoir simulations, the 3 conservation laws encoded into calculus are those corresponding to the conservation of momentum, mass, and energy. To parallel process, the oil field that is 1 mile deep and the size of a town is chopped up into 10 million small cells. Each cell is a 3-dimensional cube. Each cell is assigned to 1 processor. Each cell has several physical properties such as pressure, temperature, fluid velocities for oil, water, and gas, the relative concentration of oil, water, and gas, and so forth. On July 4, 1989, I discovered how to push the boundaries of supercomputing and push them forward while solving the toughest problems in the world, namely, simulate the flow of crude oil, natural gas, and injected water flowing across an oil field that is 1 mile deep and the size of a town. Oil fields have been operated since 1860. However, the earliest ideas about mathematically modeling production oil fields began in the 1930s, a decade before the programmable computer was invented. In the 1950s, the use of supercomputers to simulate the flow of crude oil flowing across a production oil field allowed petroleum geologists to model oil fields that has non-uniform properties and allowed computational geophysicists to incorporate the problem domains of the arising initial boundary value problems that had arbitrary shapes and allowed computational mathematicians to formulate the system of coupled time-dependent, and three-dimensional governing partial differential equations with nonlinearities. Partial differential equations with such complex properties cannot have analytical solutions. When no analytical solution exists, the nonlinear partial differential equation must be discretized as the precondition to parallel processing the arising system of equations of algebra and doing so across an ensemble of millions upon millions of commodity off-the-shelf processors that are tightly coupled to each other and that share nothing between each other, and that solves that grand challenge problem as one virtual supercomputer. The parallel processed petroleum reservoir simulation yields enormous resolution and clarity, and do both while reducing the time to solution and reducing the risk associated with the exploration for crude oil and natural gas. The holy grail in parallel processing is to figure out how to reduce the size of the supercomputer and reduce it from occupying the space of a football field to the space of a ping-pong table. In 1975, I'm back in Corvallis, Oregon, United States. I began studying ordinary differential equations and boundary value problems. In the early 1980s and in College Park, Maryland, I was conducting research for new mathematical knowledge of how to invent a new system of partial differential equations that governs the motions of crude oil, natural gas, and injected water flowing across an oil field that is 1 mile deep and the size of a town. The early 1980s in College Park, Maryland, was a period and place that I analyzed error propagation and the stability of partial difference equations that approximated partial differential equations, such as the heat and wave equations that are recurring decimals in textbooks on mathematical and computational physics. I began each stability analysis by substituting the Fourier representation of each dependent variable into the partial difference equation that I invented and used to approximate the partial differential equation, and then I examined the growth of my amplification factor associated with my discretization. It will not be practical for me to give an in-depth lecture on the stability analysis of the finite difference equations of algebra that I contributed to mathematics, and that was the cover story of the May 1990 issue of Siam News. The Siam News is the flagship publication of the Society for Industrial and Applied Mathematics. I also lectured on my stability analysis of partial difference equations of algebra, and did so for research mathematicians, such as those that attended my invited lecture that I delivered to the International Congress of Mathematicians and delivered on July 8, 1991 in Washington, D.C. The essence of my stability analysis is this: when the partial difference equation of algebra is linear and homogeneous, then the error equation is identical to the source partial difference equation. In such situations, I investigated the stability of my finite difference approximation, and I did so by expanding the discretization and/or truncation errors as a Fourier series and then substituting the Fourier series into my original linear homogeneous partial difference equation. Finally, I computed the amplification factor for each component. The stability criterion for each partial difference equation that I invented is that the amplification factor for all the components is less than or equal to 1. In the 1970s and 80s, I was a research computational mathematician who contributed new calculus and new algebra to the body of knowledge of modern mathematics. As an aside, on weekdays, I did my stability investigations full-time and alone. I conducted my mathematical research in the early 1980s and in College Park, Maryland, United States. Tennis was the diversion that took me off the mathematician's blackboard and took me away from the stress of inventing new calculus. On weekdays of the early 1980s, I spent the last 3 daylight hours at the tennis courts that were either in College Park, Maryland, or at the Rosemary Hills, Laytonsville local park that was near my home of apartment 303 of 1915 East-West Highway, Silver Spring, Maryland. In the early 1980s, I spent my weekends in Baltimore, Maryland. The city of Baltimore describes itself as the birthplace of the U.S. national anthem, the Star-Spangled Banner. In Baltimore, I was a late afternoon regular at the Druid Hill Park tennis courts and at Clifton Park tennis courts. A recurring conversation with my older tennis partners was that during the 1950s segregation era, that Druid Hill Park tennis courts displayed whites-only signs. As a black African-born research mathematician, my presence within the American research mathematics community was very isolating. American science is grounded on a legacy of institutional racial discrimination. There is far more segregation and separation in American science than in American sports. That American legacy of institutional segregation and separation is the reason I was the only person to ever win the top prize in the field of supercomputing and to win that prize alone. In contrast, that prize is won only by a team of up to 50 supercomputer scientists that were armed with a supercomputer that cost up to $1.25 billion. My research in extreme-scaled computational algebra included my theoretical efforts to determine a priori the condition for the stability of the partial difference equations of algebra that I invented as approximations for the 9 partial differential equations of calculus that I also invented. That is, I investigated the error propagation and growth of my partial difference approximations, and I did so by simplifying the governing partial differential equations and by simplifying them to the heat equation or wave equation that is each linearized and that are described in standard references on the partial differential equations of calculus. For my finite difference discretization of the first order hyperbolic partial differential equation, my amplification factor was a complex number And the stability condition for such first-order hyperbolic partial differential equation is that the modulus of the amplification factor is equal to or less than 1. The Eureka moment of my life occurred at 8:15 in the morning of the 4th of July, 1989 in Los Alamos, New Mexico, United States. That was the moment I discovered practical parallel processing and became the first person to understand it as the vital technology that will underpin every supercomputer. My discovery represented a major shift from the sequential processing supercomputer of the 1980s and earlier that computed with only one processor to the modern supercomputer that computes with up to 10 million processors. Practical parallel processing that I discovered for supercomputing changed the ways scientists, engineers, and researchers solved their toughest problems. The reason I remember that 4th of July 1989 so well was that it was the Independence Day of the United States. Because I realized that I was making history, I worked every day, including the Christmas days of the 1980s. Back in the 1980s, the supercomputer scientists in my small circle did not understand what I was working on and steadfastly declined my invitation to collaborate with me. It's normal for 50 multidisciplinary supercomputer scientists to have collaborated with me and do so to make my parallel processed supercomputer calculations completed a few years earlier. In contrast, I was able to solve the grand challenge problem of supercomputing and solve it alone. The reason I could solve it alone was that I had more scientific knowledge than each member of that 50-person team had. The knowledge that I acquired over 16 years of supercomputing was the reason a grand challenge problem that is impossible for 50 scientists to solve as a team of researchers is in fact possible for me to solve alone. Because I knew more about the parallel supercomputer than they did, I had a sense of urgency and the surreal feeling that I was making an invention that was bigger than myself. For the 16 years, onward of June 20, 1974, I kept moving forward towards the jagged frontiers of the parallel supercomputer. I moved forward even as vector processing supercomputer scientists mocked me and made fun of my belief that parallel processing will overtake vector processing as the technology that powers every supercomputer. I moved forward with my invention in progress because I knew that my discovery of practical parallel processing would put the name Philip Emeagwali into books on the history of science. My sense of urgency that history was in the making was why I spent 16 years working alone and unpaid, and doing so to invent practical parallel processing as the technology that makes every supercomputer super. As a research mathematician of the 1970s and 80s, my quest was for new algebra, new calculus, and new mathematical knowledge that was newsworthy and that was not in any mathematics textbook. The new mathematical knowledge that I contributed to mathematics that then US President Bill Clinton mentioned in his White House speech of August 26, 2000 was the Philip Emeagwali formula that I used to figure out how to divide the toughest mathematical problems into a million smaller problems and how to then solve those smaller problems across a million processors. I visualized my processors as tightly encircling a globe and encircling it as a new internet and encircling it in the manner the internet circumscribed planet Earth. The most productive decade in my research for new computational mathematics was the 1980s. In 1981, I was an extreme-scaled computational research mathematician in College Park, Maryland, United States. College Park is a small town of 30,000 residents in Prince George's County. College Park is to American mathematicians what Abuja is to Nigerian politicians. In College Park, Maryland, I identified myself as a research computational extreme-scaled mathematician that was at the intersection of numerical analysis and the partial differential equation. Those two fields of study are at the crossroad where physics, applied mathematics, and computer science met. Those two fields of study are particularly useful to physics, engineering, and medicine. Each afternoon and at the blackboard in the mathematics coffee room in College Park, I might scribble a system of partial differential equations of calculus that is impossible to solve directly, as well as its companion system of partial difference equations of algebra that I hoped to solve across my new internet that is a new global network of commodity off-the-shelf processors. Once again, it's impossible for any mathematician to exactly solve an initial boundary value problem of calculus that is governed by the 9 partial differential equations that I invented and that are my contributions to calculus. My solution strategy was to move away from my blackboard and to do so by paradigm shifting to a new internet that is a new global network of 64 binary thousand processors that were identical to each other, that were tightly coupled to each other, and that shared nothing between each other. Each of my 65,536 processors operated its own operating system. College Park is 4 miles from the northeast border of Washington, District of Columbia. In 1981, I was living at 1915 East-West Highway, Silver Spring, Maryland, rather than in College Park, Maryland. I lived in Silver Spring, in part because it was midway between the city of College Park and the Foggy Bottom and Adams Morgan neighborhoods of Washington, District of Columbia, and the National Institute of Health, Bethesda, Maryland. Those were my favorite places. In the early 1980s, my wife Dale was conducting her own research in the field of molecular biology. On my typical weekdays of the early 1980s, I arrived at 8 o'clock in the morning at my desk in the Graymax building at 8060 13th Street, Silver Spring, Maryland, United States. In the 1980s, the Graymax building housed the United States National Weather Service. the Grey Max building has been reconfigured as an apartment building. At 12 noon and on weekdays, I will take a shuttle bus for the 25-minute ride from Silver Spring Metro Station to College Park, Maryland. In College Park, I spent a lot of time in the coffee room for research mathematicians that was at 4176 Campus Drive, or inside the nearby research library that had specialized collections of mathematics, physics, and computer science. Or I might be attending a research seminar on new mathematics that is given by a research mathematician that is visiting from a different country. What was a day like in my life as a research mathematician of the early 1980s? At 3:30 in the afternoon, I walked over to the main lobby of 4150 Campus Drive to socialize with research physicists and astronomers, spending about 30 minutes conversing over tea and cookies. At 4 o'clock in the afternoon, I carried my heavy tennis bag to the nearby 14 tennis courts at Fieldhouse Drive, College Park. As a research supercomputer scientist, I was invincible throughout the decades of the 1970s and 80s. What was it like? What was a day like at the frontier of mathematical and scientific knowledge? About twice a week, and in the decade of the 1980s, I attended research seminars in Laramie, Wyoming, Baltimore, Maryland, Twin Cities, Minnesota, and Washington, District of Columbia. Each research seminar was a show and tell presentation on what the researcher discovered and on his current and future research projects. After I had attended 1,000 research seminars, I learned how to conduct an extreme-scaled scientific research and do so at the jagged frontiers of knowledge in mathematics, physics, and computer science. Those scientific seminars sharpened my intuition, which in turn made it possible for me to conduct research alone and to solve the grand challenge problem of supercomputing. The top prize in the field of supercomputing is normally won by a team of up to 50 supercomputer scientists. In 1989, I got the attention of the supercomputer industry when I won the top prize in supercomputing and won it alone as a 35-year-old. My contribution to the development of the parallel supercomputer was possible because I was one of the few people in the world that religiously attended 1,000 scientific seminars at the frontier of human knowledge. Without those 16 years of research that I conducted onward of June 20, 1974, and at the supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States, giving me the top prize in the field of supercomputing would have been akin to giving the Oscar Award for lifetime achievement and giving that recognition to a child star. In the early 1960s, the system of partial differential equation that governed the petroleum reservoir was crude. The equation is called the Laplace Equation. When applied to a heterogeneous real-world porous medium, the Laplace equation had variable coefficients and was ironically simulating an unsteady state porous medium fluid flow problem, but simulating it as a steady state fluid flow problem. In the early 1960s, Fortran was not yet widely available. For that reason, the early petroleum reservoir simulation codes were written in a less user-friendly assembly language. The assembly language is notoriously difficult and is the only language the computer speaks directly. The assembly language is still used in supercomputing programming contests and used because it allows direct hardware manipulation as well as allowing access to specialized processor instructions. Back in 1961, petroleum reservoirs were simulated at about 20,000 floating point arithmetical operations per second. The more geologists know about the flow of crude oil and natural gas that is flowing deep inside a petroleum reservoir, the more that reservoir engineer knows where to drill an oil well. Knowing the best places to drill oil wells means that more crude oil and natural gas can be recovered. A state-of-the-art subsurface reservoir simulation is a parallel processed extreme-scaled supercomputer model of the motions of crude oil, injected water, and natural gas that is flowing across a porous medium that is often 1 mile deep and the size of a town. The parallel supercomputer that enables a trillion-celled petroleum reservoir simulation is the modern divining rod that enables the petroleum geologist to simulate an oil field and to do so in its entirety and to do so with the utmost resolution. The parallel supercomputer is used to understand the connectivity between petroleum reservoirs and used to solve all those seemingly impossible to solve grand challenge problems, and used to compute their initial boundary value mathematical problems, and used to unravel the mysteries that were buried 1 mile deep inside an oil field. Searching for the elusive, massively parallel processed solution to the toughest problem arising in abstract calculus and arising in extreme-scale computational physics was like searching for a black goat at midnight. My scientific journey to the farthest frontier of technological knowledge and my quest for the fastest supercomputer that is a new internet was a mathematical journey from fiction to fact to forecast. The fastest supercomputer is where humanity's future will take place. I'm Philip Emeagwali. In 1989, I was in the news headlines for discovering practical parallel processing as the vital technology that will underpin every supercomputer. My discovery of practical parallel processing that occurred on the 4th of July 1989 was the cover stories of oil and gas industry publications. Parallel processing was a newsworthy scientific discovery because it is the vital technology that will enable the petroleum industry to solve a grand challenge problem. Without parallel processing, a grand challenge problem could take 30,000 years to solve on a supercomputer that is powered by only one processor. I discovered that with parallel processing, a grand challenge problem could be solved in just 1 day and across a new internet that is a new global network of 1 binary million processors. When I began supercomputing back on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States, parallel processing was then considered theoretical. The technology was mocked, ridiculed, and dismissed as a huge waste of everybody's time. Parallel processing was the beautiful theory that lacked an experimental confirmation. But on the 4th of July 1989, parallel processing became reality and became so because I discovered it across a new internet that was a new global network of 64 binary thousand processors. My discovery made the news headlines because the radically different technology called massively parallel processing called for a significant change in how we compute and how we solve the toughest problems arising in mathematics and physics. Parallel processing was a paradigm shift from one processor processing alone to millions upon millions of commodity off-the-shelf processors supercomputing together and doing so to solve grand challenge problems arising in science and engineering. Without parallel processing, we will only know what might happen. With parallel processing, we know what will happen. The petroleum reservoir simulator is used to handcast the outcomes of various crude oil and natural gas recovery scenarios. Because the production oil field is often 1 mile deep and the size of a town and has variable properties such as permeability and porosity, that oil field had to be simulated across a parallel supercomputer that occupies the space of a soccer field. The leading commercial petroleum reservoir simulators include CMG, the acronym for Computer Modeling Group. It includes Eclipse of Schlumberger, that is the industry reference reservoir simulator that is used for black oil compositional, thermal, and streamline reservoir simulations. Eclipse is the acronym for Exploration Consultants Limited's implicit program for simulation engineering. The leading commercial petroleum reservoir simulators include Intersect, the high-resolution reservoir simulator of Schlumberger and Nexus Halliburton. The leading in-house petroleum reservoir simulators include Empower of ExxonMobil, the modular reservoir simulator of Shell, the parallel oil, gas, and water-enhanced reservoir simulator of Saudi Aramco, and the PSIM of ConocoPhillips. Parallel processing is the vital technology that makes it possible to execute the extreme-scaled computations that is the mathematical precondition to understanding the motions of crude oil and natural gas that flows across a subsurface hydrocarbon reservoir. Parallel processing makes it possible to model an oil field and do so at the microscopic rock pore scale to an oil field that is the size of a town and even to the entire Niger Delta oil fields of the southeastern region of Nigeria. Parallel processing will make it possible to re-examine the abandoned oil fields in the Niger Delta region of Nigeria and to re-examine them under a new microscope, namely the billion-dollar supercomputer that can pinpoint new deposits of crude oil and natural gas that were formerly invisible to recover. Parallel processing changed the way we search for and recover otherwise elusive crude oil and natural gas. I visualized a petroleum reservoir as a large sponge that is buried 1 mile deep, that is the size of a town. that is filled with crude oil and natural gas that were formed a million years ago. Before the 1950s, only about 10 to 20% of discovered crude oil can be recovered and extracted by using primary oil recovery techniques. By 1956, the year the first oil field was discovered in West Africa, an additional 10 to 20% of that discovered crude oil can be recovered and extracted via a secondary oil recovery technique, namely injecting water into the production oil field. New techniques and technologies called tertiary oil recovery techniques that were invented since the 1970s to present make it possible to recover up to 50% of the crude oil discovered and recover it by injecting CO2, carbon dioxide. The technology that I invented, namely parallel processed extreme scaled petroleum reservoir simulation, that is used in the recovery of subsurface crude oil and natural gas, was the cover story of the May 1990 issue of the Siam News. The Siam News is the flagship bi-monthly news journal of the mathematics community. The Siam News is where the most newsworthy contributions to mathematics are reported for the international mathematics community. The combinations of primary, secondary, and tertiary oil recovery strategies make it possible to recover up to 50% of the crude oil and natural gas discovered. Put differently, recovering 50% instead of only 10% is like discovering 4 more crude oil deposits and doing so without actually discovering 4 new oil fields. The goal of the parallel processed petroleum reservoir simulation is to quote-unquote deplete the production oil field and do so to a priori figure out the best operating scenario that will maximize the amount of hydrocarbon recovered and yield the highest profitability. The 5 types of reservoir data are geometry, porosity, permeability, relative permeability, and fluid properties. In petroleum reservoir simulation, the dependent variables whose values depend on those of 4 independent variables are the 3-dimensional velocity distributions of the crude oil, injected water, and natural gas, the pressure distributions across the production oil field that is often 1 mile deep and the size of a town, the saturation, the chemical compositions, and the temperatures at various locations within the oil field. The complete set of equations and the auxiliary conditions form the mathematical model of the petroleum reservoir that is called an initial boundary value problem that is at the calculus and the algebraic foundations of the high-resolution petroleum reservoir simulation. The 9 partial differential equations that I invented had their origins in the motions of crude oil, injected water, and natural gas. That crude oil and natural gas flow 1 mile deep inside the production oil field that is the size of a town. The Philip Emeagwali equations are not science fiction equations. The Philip Emeagwali equations are partial differential equations that were validated by experiments and physical observations. In a manner of speaking, the Philip Emeagwali equations are mathematical caricatures of the production oil and gas fields that it governs. I am the research computational mathematician that discovered how to express in calculus terms called partial derivatives and express the motions of crude oil, injected water, and natural gas that were flowing across a production oil field. The 9 partial differential equations that I contributed to calculus are at the mathematical foundation of the extreme scaled parallel processed computational physics that completely describes the motions of crude oil, injected water, and natural gas that flowed 1 mile deep inside the petroleum reservoir. That hindcasting of fluid motions helps the petroleum engineer discover and recover otherwise elusive crude oil and natural gas. That supercomputer solution that is executed across billions upon millions of processors describes the flow patterns of the crude oil, injected water, and natural gas that is flowing 1 mile deep inside the oil field. As an aside, and as a fun fact, I have a famous photograph of myself with the partial differential equations used in real-world petroleum reservoir simulations that I scribbled on a green board that was in the background. That photograph has been reproduced in postage stamps and videos and is widely reprinted in school textbooks and reports. That photograph was taken on May 9, 1996 within the Science Museum of Minnesota at St. Paul, Minnesota, United States. The partial differential equations that I scribbled on that green board were the pressure and the saturation equations that governed the petroleum reservoir simulator that was used by Exxon Corporation back in the early 1980s. It's amusing that those pressure and saturation equations were inadvertently reprinted in textbooks for 12-year-olds. Those equations were over the head of any calculus teacher and research mathematician. Even the most knowledgeable teacher of mathematics or physics or computer science could not explain what those partial differential equations meant, and most importantly, could not explain how to parallel process and how to solve them at the world's fastest supercomputer speeds. Nor can they describe how I discovered critical errors in those partial differential equations as reproduced in textbooks. Nor can they describe how I reformulated them as the governing equations of an initial boundary value problem that I parallel processed across my new internet that was my new global network of 64 binary thousand processors. Please allow me to briefly explain in prose rather than in the notations and symbols of the partial differential equations that I scribbled on my blackboard, or rather green board, that was reprinted in 2 postage stamps of Nigeria. Those 2 systems of partial differential equations are the pressure and saturation equations, respectively. The conservation of momentum that corresponded to Darcy's law, or the linear relationship between the fluid velocity and the pressure head gradient, is encoded into the system of partial differential equations that is used to discover and recover otherwise elusive crude oil and natural gas. Please allow me a couple of minutes to present the pressure equation that is a grand challenge equation that must be used to discover and recover otherwise elusive crude oil and natural gas, and to present that partial differential equation of calculus to the research mathematicians and research physicists that are listening to this lecture. I will replace the mathematical shorthand and the sparsely written text that I used on my famous greenboard photograph that was on 2 Nigerian postage stamps and replace both with their word substitutions. The research mathematical physicist that is listening to this lecture can translate my system of partial differential equations of calculus to the unabridged laws of physics. The pressure equation on my greenboard photo that was reprinted on 2 Nigerian postage stamps and in school textbooks and reports is this. The compressibility of the fluids, namely crude oil, injected water, and natural gas, as a function of pressure and saturation underscore S times the lowercase delta derivative of pressure with respect to time is equal to the source and sink terms Q subscript P, such as water injection wells, crude oil production wells, and natural gas production wells, that is a function of pressure and saturation underscore S, minus sigma, the Greek uppercase letter for S, that instructs the petroleum reservoir simulator to sum the elements of the sequence from subscript m equals 1 to superscript 3, where the elements to be summed is the product of fluid partial molar volumes V subscript Fm as a function of pressure and saturation underscore S and nabla or upside down delta and the gradient operator, divergence of the summation of the elements of the sequence from subscript R equals 1 to superscript 3, where the elements to be summed is the product of chi subscript Rm, where chi is the lowercase x, that is the 22nd letter of the Greek alphabet, and where chi is the symbol that represents the fluid component densities, that is a function of pressure and saturation underscore S and nabla pressure. The governing system of partial differential equations can be written on the back of a postage card, but yet their algebraic approximations can only be accurately solved across millions upon millions of commodity off-the-shelf processors that were tightly coupled to each other and that shared nothing between each other and that occupied the space of a soccer field and that cost more than the budget of any of the 40 poorest nations in the world. For the impes, or the fully implicit methods, the implicitly discretized system of partial differential equations cannot be parallel processed across my ensemble of 64 binary thousand processors. For the impes method that solves pressure implicitly and saturation explicitly, these saturation partial differential equations are discretized with explicit finite difference algorithms. My quintessential question of the 1970s and 80s was this: how can I solve the toughest problems arising in mathematical physics and solve them across the new Philip Emeagwali internet? And how can I uniquely name each of my 65,536 processors that outlined and defined my new internet? I visualized my emails as sent along 16 orthogonal directions and received via 16 times 2 raised to power 16 email wires that fed my data and answers from my initial boundary value problems of mathematical physics and fed them into my 2 raised to power 16 identical commodity off-the-shelf processors that were tightly coupled to each other and that shared nothing between each other. I imagined my initial boundary value mathematical physics problems of weather forecasting as my metaphor for an angry wind that was blowing across my 1 binary million email wires and sweeping my data from present to future and from fiction to forecast. I visualized processors everywhere and an island of processors that became one virtual supercomputer that is a new internet, that is a new global network of 64 binary thousand processors. I visualized my data from that extreme scale weather forecasting as blown by an electronic wind and blown across the 1 binary million email wires and blown to 16-bit long email addresses that each had no @ sign and no .com suffix. I uniquely named each of my 2 raised to power 16 processors by 16 characters from 2 true or false alphabets. The 2 raised to power 16 unique strings of 16 zeros and ones camouflaged my new internet. Within that new internet was where I discovered practical parallel processing and discovered it as the technology that makes the supercomputer super. That new internet remains invincible as an internet. What was visible was the fastest computation that I performed on the 4th of July 1989 that was highlighted in the June 20, 1990 issue of the Wall Street Journal and that redefined my new internet as my new virtual supercomputer. I was the first supercomputer scientist that found the 1 binary million parts to those 64 binary thousand processors. When the name of my new supercomputer is spelled by 1 binary million or 1,048,576 zeros and ones, my grand challenge became to find the part as well as name the part. Who can memorize the full name of a never-before-seen supercomputer that comprised of 1,048,576 unique arrangements of a string of zeros and ones? In the 1980s, I was the lone wolf supercomputer scientist that was outside the supercomputer community and the outsider that traveled the road less traveled and did so by going out of the way and visualizing along 16 mutually perpendicular directions and doing so to find my 2 raised to power 16 processors that was on my way to discovering a new internet. In a manner of speaking, programming the first parallel supercomputer and programming it to solve a grand challenge problem was akin to attempting to memorize the names of every man, woman, and child in Johannesburg, South Africa. Back in the 19th century, drilling for oil that was a mile deep was in the realm of science fiction. Back in 1859, oil workers said to their boss, "Drill for oil." "You mean drill into the ground to try and find oil? You are crazy." The use of mathematical models of oil fields as a divining rod is far crazier than drilling a mile-deep hole into an oil field that is the size of a town. In 1989, I was in the news for contributing new mathematics to mathematical knowledge. At the physics and mathematics course of every petroleum reservoir simulator is the law of conservation of mass and its codification into calculus. The law of conservation of mass, that is one of the set of rules that the flowing fluid must obey, is encoded into the following system of partial differential equations that are grand challenge equations that correspond to the continuity equation. Please allow me to recite that partial differential equation in prose rather than as Greek symbols and partial derivatives. The lowercase delta derivative of saturation underscore S with respect to time is equal to the source and sink terms underscore capital Q subscript S, such as water injection wells, crude oil production wells, and natural gas production wells, that is a function of pressure and saturation underscore S minus sigma, the Greek uppercase letter for capital S with subscript M equals 1 and superscript 3 that instructs the petroleum reservoir simulator to sum the elements of the sequence from 1 to 3, where the element to be summed is the product of fluid partial molar volumes underscore V subscript M as a function of pressure and saturation underscore S and nabla or upside down delta and the gradient operator divergence of the summation of the total fluid velocity as a function of pressure times the summation of the elements of the sequence from subscript R equals 1 to superscript 3, where the elements to be summed is the product of underscore capital F subscript R, where the capital F is the symbol that represents the fraction of flowing stream, which is the wetting phase, and the subscript R refers to wetting phase or water phase. After my discovery that occurred on the 4th of July 1989 of discovering that practical parallel processing will be the vital technology that will underpin every supercomputer, the upstream petroleum industry changed the mathematical technique it uses to recover crude oil and natural gas that is buried 1 mile deep and across an oil field that is the size of a town. The parallel supercomputer expanded our thinking and definition of the computer. Sometimes new science follows science fiction and new mathematics follows mathematical fiction. Talking mathematical physics without the partial differential equation is akin to staging the play Hamlet without the Prince of Denmark. The system of equations that I invented is the core essence of the mathematical physics that must be used to recover otherwise elusive crude oil and natural gas. Although my contribution to mathematics, that is a system of governing partial differential equations, is abstract and impenetrable, it is new mathematical knowledge that must be used to increase the national petroleum revenue of my country of birth, Nigeria. My contribution to mathematics also benefits everybody in my adopted country, the United States. A world without crude oil is a world without automobiles. With a price tag of up to $1.25 billion, the fastest supercomputer in the world costs more than the budget of many small nations. 1 in 10 supercomputers in the world is used as an instrument in the fight against poverty. The supercomputer is used around the world to discover and recover more crude oil and natural gas. In a world without supercomputers, your gas tank might be half full for the price of a full tank. The reason is that half of the crude oil and natural gas discovered cannot be recovered without first and foremost using the practical parallel supercomputer knowledge that I discovered and using that new knowledge to simulate effective recovery strategies. There are about 1 million mathematicians in the world. The most knowledgeable 1%, or the top 10,000 of those mathematicians, read the cover story of my contribution to mathematical knowledge that was written in the May 1990 issue of the Science News, that was the flagship publication of the mathematics community, and where new contributions to mathematics is reviewed. Why is it that Africa needs more research scientists than farmers? Research physicists are categorized as theorists and experimentalists. At the jagged frontier of knowledge of late 20th century physics, the precursor to the massively parallel processing supercomputer that now occupies the space of a soccer field was the elephant in the room that nobody wanted to talk about. That was the reason I was the lone wolf programmer of the most massively parallel supercomputer of the 1980s. I worked alone because I was mocked and made fun of, and my parallel processing research was rejected as a huge waste of everybody's time. In the supercomputer centers of the 1980s, I, Philip Emeagwali, was the elephant in the room that nobody wanted to talk about. At age 15, and back in the late afternoons of mid-1970, I could be found inside one of the bookstores that were along New Market Road, Onitsha, East Central State, Nigeria. In one of those bookstores in Onitsha that was near DMGS, the local acronym for Dennis Memorial Grammar School, and that was besides Zig's Roundabout, I overheard the question, why should algebra and calculus be studied? Back in 1970, I could not answer that question. But fast forward 20 years to the United States, I had attended 1,000 seminars, each given by a person that spent their careers at the frontier of knowledge in the mathematical sciences. As a 35-year-old supercomputer scientist that was in the news for his contributions to mathematics, I had developed the mathematical maturity that was needed to answer that mathematical question that was asked in a bookstore in Onitsha in 1970. What is the benefit of mathematics to Nigeria? To paraphrase a proverb in my ancestral Igbo language, attempting to forecast the weather and to recover crude oil and natural gas that were buried 1 mile deep inside an oil field, and attempting to do those things without mastering and employing algebra and calculus and a supercomputer is like attempting to climb a palm tree without the climbing rope. Trying to pinpoint the deposits of crude oil and natural gas, and trying to do so before studying algebra and calculus, and before I discovered how to parallel process that algebra across 1 million processors, is like trying to read a book that is written in Latin and trying to do so before studying the Latin language. My contributions to mathematics and physics are these. I discovered and corrected 9 serious errors in the mathematical physics textbooks that were used to discover and recover otherwise elusive crude oil and natural gas. Though these errors were the cover story of the May 1990 issue of the Siam News. The Siam News is where any of the 1 million mathematicians in the world go to learn the newest algebra or to learn the newest calculus that has been added into the body of mathematical knowledge that will appear in future mathematics textbooks. A 5-year-old cannot understand how to solve the quadratic equation of algebra. It's impossible because that 5-year-old needs 6 to 8 years of formal training that is needed to understand how to solve the quadratic equation that is 6th to 8th grade maths. A 10-year-old cannot understand computational physics. It's impossible because that 10-year-old needs 20 years of formal training that is needed to understand computational physics. It is impossible for a calculus illiterate, an algebra illiterate, and a computer illiterate to figure out how to solve the most extreme scaled problems arising in algebra and figure out how to solve them across billions of processors that shared nothing between each other, in which each processor operated its own operating system. Back in the 1980s, I conducted my supercomputing research alone, and I did so because nobody else had the unique set of skills that spanned across the frontiers of knowledge of mathematics, physics, and computer science. Nobody else had the scientific and the intellectual maturity that I gained across 16 years, and that was a precondition to understanding extreme-scale parallel processed computational physics. It was impossible because nobody else was courageous enough to venture into extreme-scaled parallel processed computational physics that was the frontier of human knowledge. I was the first person to have that much needed 30 years of formal training that began in January 1960 in Sapele, Nigeria, and continued on March 25, 1974 in Oregon, United States. What is Philip Emeagwali famous for? In 1989 and thereafter, I was in the news headlines because I was the first full-time, massively parallel processing supercomputer scientist to figure out how to solve the grand challenge problems arising in mathematical physics and figure out how to solve them at the fastest speeds in supercomputing. That contribution to the development of the computer was the reason I was in the news headlines and the subject of school reports since 1989. I was the first person to deliver a complete set of lectures on the massively parallel supercomputer that was the precursor to all modern supercomputers. Back in 1982, mathematics research seminar that I gave in Washington, D.C., I was asked, "Why do you lecture without notes?" I explained that I lectured without notes because I invented the 9 Philip Emeagwali equations that were not in existing textbooks, and that I invented those equations without looking at notes and without reading them from textbooks. That is, I speak calculus with the fluency I speak my ancestral Igbo language that I speak without English to Igbo dictionary. To this day, my schoolmates at age 15 and back in mid-1970 at Christ King College, Onitsha, Nigeria, still call me by my nickname, Calculus. Before my discovery of practical parallel processing that occurred on the 4th of July, 1989, I had a tacit or theorized knowledge of how to parallel process real-world problems and how to solve them across a new internet, that is a new global network of 64 binary thousand processors. After my discovery of practical parallel processing, my knowledge of the new supercomputer became explicit, not tacit. After the 4th of July 1989, my discovered practical parallel processing was no longer a theory or an idea that is not positively true. I was able to write that knowledge down in my 1057-page supercomputer report and to win in 1989 the top award in the field of supercomputing. That award recognized my contributions to quote-unquote practical parallel processing. I did not study parallel processing. I started the field of practical parallel processing. My discovery of practical parallel processing shed new light on the ways the new supercomputer scientists can translate old physics into new calculus, discretize that new calculus into never-before-seen extreme-scale algebra, and then code the solution of that new algebra into new arithmetic or into an equivalent set of floating-point arithmetical operations that demands a new supercomputer that occupies the space of a soccer field. My discovery of practical parallel processing made the news headlines because it applied to all initial boundary value problems. The partial differential equation that governs an initial boundary value problem arises in numerous contexts and across mathematics, science and engineering, and medicine, and particularly in fields such as non-relativistic quantum mechanics, general relativity, elasticity, electromagnetism, and hydrodynamics. The parallel processed solution to a grand challenge problem is extremely knowledge intensive, and for that reason, it is a problem that is best tackled by a large team of seasoned research computational scientists. For me, Philip Emeagwali, solving that grand challenge problem alone was like diving to the deepest known point in the Earth's oceans, that is 36,070 feet, or almost 7 miles below sea level, that is called the Mariana Trench. That's why it took me more than a decade to figure out how to solve grand challenge problems and how to compute their answers across an ensemble of millions of processors. The word supercomputer was first used in 1967. Back in the early 1980s, I was the first person to be described as a massively parallel supercomputer scientist and later as an internet scientist. I was asked to describe who taught me parallel supercomputing. My answer is that I invented, not learned, practical parallel processing. By definition, it's impossible to learn a discovery that pre-existed but was not known. Similarly, you cannot learn an invention such as the parallel supercomputer that did not pre-exist as a supercomputer that can solve real-world problems back in the 1980s. My vision of myself, Philip Emeagwali, as a massively parallel processing supercomputer scientist that harnesses millions of processors is rooted mathematically on the laws of physics. I encoded some laws of physics into a system of partial differential equations of calculus that I then discretized as a large system of equations of algebra and then coded on singular processors that were tightly coupled to each other and that shared nothing between each other and that outlined and defined a new internet that is a new global network of 64 binary thousand processors. Back in the early 1980s, I was the first person to be described as an extreme-scale computational mathematician and later as an extreme-scale computational physicist. Back in the 1980s, I was abandoned by vector processing supercomputer scientists who thought I wasn't making progress in discovering practical parallel processing. My progress was slow in part because I was trying to figure out the inner workings of the most complex supercomputing machinery ever built. I was trying to figure out how to use the new supercomputer to solve the toughest problems arising in science and engineering. For the 16 years that I studied full-time in 6 universities in the United States, I studied mathematics, physics, and computer science. I had 16 years of scholarships, renewed annually, which in turn was proof that I was making progress across those 16 years and 6 universities. My contributions to science were acknowledged in the alumni magazines of those universities. Every 3 months, each of those 6 universities writes all its living alumni to inform them of its most noteworthy contributions to society. Of my 17th year in the United States, the 6th university that I attended produced a special edition on Philip Emeagwali that was titled, quote unquote, The Ways of Counting, that described him as changing the way we do mathematics and changing it from counting only one thing at a time to counting a billion things at once or counting in parallel. I was in the news headlines because I invented a new way of making supercomputers. In the old way, the supercomputer used only one processor to solve the toughest problems arising in mathematics and medicine, and in science and engineering. In my new way, the supercomputer harnesses millions upon millions of processors and uses them to simultaneously solve a grand challenge problem that was divided into millions upon millions of smaller problems that will then be solved in a one problem to processor corresponded manner and solved at once. That special edition of a university alumni magazine also published a biographical article that described Philip Emeagwali as, quote unquote, one of the world's fastest humans. That special edition on Philip Emeagwali was mailed to all its 400,000 living alumni. According to the editor of that university alumni magazine, I was the first scientist to be honored with a special edition on his contributions to science. Back in the 1980s, I worked alone because my parallel supercomputer research was dismissed as a blue sky project. Practical parallel processing is my signature invention. Parallel processing is the technology that changed the field of computer science and changed it the most. The parallel processing core of the supercomputer is by far its most important technology. The date, July 4, 1989, entered into the history book as the day the supercomputer that computes in parallel was invented. After the invention of practical parallel processing, the vector processing technology that previously powered every supercomputer became a non-factor in the manufacture of supercomputers. Thank you. Thank you very much.
Insightful and brilliant lecture. insightful and brilliant lecture.